Good evening, Professor Noble. I'm Noel Anderson. Giving this a second shot here. I went through and checked the files that I'd sent over and some of the dud files that I scrapped beforehand, and none of them had the audio. So thanks for giving me a chance to re-record this. So this is the presentation on my hypothetical universe. I named it Omicron Persei IA. It's a mouthful, so I'll probably just refer to it through the rest of the slide as my DIY universe. So this presentation, I'll be leading us through the sequence of events much like it's described in the syllabus. So start out with Omicron Persei versus the benchmark model and what that looks like on the power spectrum. Next, I'll go into parameter exploration and kind of the ratios and the parameters of my universe versus the benchmark model. Next, I'll go through expansion history and kind of the different checkpoints that the universe that I created would hit during certain points in time and how that compares to our own universe. And finally, I'll end with the universal plot and where my universe matches up on the universal plot. So Omicron Persei IA. The numbers that I input for my DIY universe are on the left-hand side there. For normal matter, I put 0.35. Dark matter consists of 0.45 or 45%, and then dark energy consisted of 0.2 or 20%. And so relative to our universe, in which baryonic is at 5%, dark matter 27.5%, and dark energy 67.5%, at least as far as this model goes, to make it repeat what our universe says, you can see that the power spectrums are different. And on my power spectrum for my DIY universe, which is the right-hand image, the peak is significantly higher. And I'll talk about what that means here in a second for the image below. The graph appears to be shifted to the right as well. And our own universe, it has these double peaks. And my DIY universe, it doesn't really have those double peaks. It kind of has one major peak after the big one, and then it kind of dies off. There's a little blip there, but it goes down real quick. So the difference in the cosmic microwave background between the two universes. So like I said, that massive peak, I believe, is what is leading to my universe on the right having extremely larger, or not larger, but darker spotting. So you see, I think the most significant one is the dark red spot there at the bottom. Compared to our own universe, it's a lot larger. The blue spots are also much more significant. And what this means is there's basically regions of the CMB that are much hotter. They're almost like heat sinks, heat holes. So both images are scaled into 1 degree. If they were scaled in further, say if we zoomed in on that dark red dot, we would actually see little specks of blue, and the same goes with the blue dots. This is just kind of a zoomed out image in which the anisotropies are plotted kind of as an average over the area. So parameter exploration. I'm actually kind of surprised the click-through is working here. It wasn't when I tried earlier. So the baryon to photon ratio, which is this first image, I calculated it to be 4.43 times 10 to the negative 9th, which is 7.3 times higher than our own universe. The recombination temp that I calculated for my universe using that baryonic ratio was 8,205. The scale factor of my universe came out to be 1.42, and the redshift came out to be negative 2.96. So a little strange. I remember people talking about this in the discussion, how the Z actually came out to be negative, which would indicate a blue shift. And the redshift and scale factor of matter radiation equality is the last slide here. So the scale factor at MR equality would be 2.57 times 10 to the negative 4th, which is real small, and the redshift would be 3,888. Is dark energy important in my universe? So important to me means that dark energy is the dominant factor. And so I calculated the time of dark energy matter equality, which came out to 15.6 billion years. So in terms of our own universe, dark energy is not significantly important. If our universe was about 2 billion years older, then it would be significant. So next was to choose a time period and describe the quantities of that time period. So the time period that I chose was a time between radiation matter equality and matter dark energy equality. So a time between 2.67 million years and 15.6 billion years. And I just mapped out the parameters through that time. So at radiation matter equality, the redshift would be 3,888, and at matter dark energy equality, it would be negative 1.67, the blue shift. These numbers seem very different from one another to me. If they're correct, then it would make sense to me that the universe is extremely redshifted there early on because it's rapidly expanding, and at the time of matter dark energy equality, the universe is actually contracting, so there's a bit of a snapback there. The scale factor would be between 2.57 times 10 to the negative fourth and 1.2 at this time. So now that I had those parameters lined out, I decided to choose a point in time between both of those, and the redshift that I chose for myself was just 9. They kept the math pretty simple here. So with a redshift of 9, the scale factor came out to be 0.1, and running that through the Friedmann equation gave me a Hubble expansion rate of 1,312 kilometers per megaparsec per second. And using that, I was able to calculate the critical density of 1.71 times 10 to the 6 mega electron volts per meter cubed. So plugging this into the universal plot from Ryden, this is kind of interesting to me. So the simulator was telling me that my universe was a flat universe, and when I plug it into here, obviously this is just the dark energy parameter on the left, and the dark, or not, sorry, not dark, but the matter parameter on the bottom. And that red dot there kind of indicates where my universe would fall on this plot. So it doesn't fall on the flat line, it falls beneath it, and it falls within the baryonic acoustic oscillation sphere. So it's not within S&E or CMB area, and it does not fall within the no Big Bang area. And thank you for your time. Sorry I had to re-record this, and hopefully none of this was too jumbled up. So have a good night.